Okay, let's take up another example. We can see that I have been given another recursive function. Now, where is the recursive call? The recursive call is present here. The recursive call is present here. Now, in the previous example, we saw that the recursive call was present at the end, so we called it a tail recursion. Here, the recursive call is neither present at the end, nor is it present at the beginning. So, this is an example of body recursion. This is an example of body recursion. Okay, fine. Now let's try to trace this out. We have been asked to take the value of n as 3. So since this is a short piece of code and the value of n is also quite small, I'll use the tree method. So I'll start with a of 3 as my root and I'll try to trace it out. So a of 3, now 3 is greater than 0, you come inside, you have to print. So you have to print 3 because n is 3, so you print n, so n is 3 now, so you print 3. And here you make a call to n minus 1. What is the value of n? The value of n is 3. So you make a call to a of 2. And then there is another printf statement. So you make another print on 3. Now a of 2, there is an a of 2, so you need to expand on this. So let's expand. Is 2 greater than 0? Yes. So you print. What do you print? You print n. That means you print 2. And then you invoke a of 1. So you invoke a of 1 and then you print n. So what do you print? You print 2. And then there is a of 1. So is 1 greater than 0? Yes. So you print n. So you print 1 and then you invoke a of n minus 1. What is n? 1. So you invoke a of 0 and then you print n. What is the value of n? The value of n is 1. So you print 1. Now finally, when a is 0, is 0 greater than 0? No. So the condition is not satisfied. As a result, it terminates. Now we no longer need to expand this tree. Now let's try to trace out this entire tree top down, left to right. We will trace out this tree in the order of top down, left to right and find the output. So let's see what the output will look like. So now for a of 3, I can see that first there is a print. So I'll print 3. Now I have to cover its breadth. So now I can find an a of 2. So I'll try to expand it. So for a of 2, I can see that there is a printf on 2. So I'll print 2. Now on trying to expand this, I find that there is an a of 1. So I'll have to expand it. So I'll have to print 1. So I print 1. And then on trying to expand a of 0, I find that there is nothing else for a of 0 to contribute to. So I go back up and then I look at printf 1. So I'll print 1 and then again I go back up. Now on going back up, I see that I have completely covered a of 1, but there is another branch from a of 2. So I have to cover that. So I'm trying to cover the branch of a of 2. I find that there is a printf statement. And what is the statement? Printf 2. So I print 2. And then again I go back up. And now I see that I have covered a of 2 completely, but there is a branch of a of 3, so I have to cover that. So I have to print 3. So I'll print 3. And on printing 3, again I go back up and I see that I have completely covered the root, which is a of 3. So my output is 3, 2, 1, 1, 2, 3. So this is how you can trace out a recursive function. Now, if you are trying to find the number of function calls that have been made, you can just count them. So how many function calls have been made? So there is a function call on a of 3. There is a function call on a of 2. There is a function call on a of 1. And there is a function call on a of 0. So for n equal to 3, we have made 1, 2, 3, 4 function calls. That means for a value of k, I have to make k plus 1 function invocations like we saw in the previous example. If you'll remember this example, we made 4 invocations for n equal to 3. So we can say that for k invocations, we have to make for n equal to k, we have to make k plus 1 invocations. Similarly, here also we can see that for n equal to k, we have to make k plus 1 invocations. So this is how you would trace out a recursive function. I'll take up another example. Now let's take up this example. Okay. So here we can see that there is a recursive call at the beginning as well as a recursive call at the end. So here, this is an example of a mixed recursion, right? We cannot classify this recursion as either head recursion or tail recursion. This is an example of a mixed recursion. Now let's try to trace out what would happen, what would be the output for n is equal to 2. Let's see. So for a of 2, what do? We check. Is 2 greater than 0? Yes. So we have to make a call to n minus 1, a of n minus 1. What is n? N is 2. So n minus 1 is a of 1. We'll have to make a printf statement. So we have to print the value of n. What is the value of n? 2. So we print 2. And we have to make a call to a of n minus 1. So n is 2, so a of 1. Now I have to expand this. So a of 1, now see, for a of 1, again I have to check this condition. Yes, it's satisfied. So I come inside and I make a call to a of 0. And then I make a printf statement. So what do I print? I print n. What is the value of n? The value of n is 1. So I print 1. And I make a call to n minus 1. So what is n minus 1? A of 0. Similarly, I expand a of 1 again. So I'll get a call to a of 0, a printf on 1, sorry about that, a printf on 1, and another call to a of 0. Now since a of 0, for how many a of 0 function calls are there? 1, 2, 3, 4. For each of these, we can see that this condition will not be satisfied. As a result, we no longer need to expand our tree. Now we need to trace out this tree in top-down, left-to-right fashion. So I'll start from a of 2, I'll go to a of 1, I'll go to a of 0. Now I have to traverse this a of 1 completely. I have to cover its breadth. So I go back up and then I find a printf statement. So I print 1. And then again I go back up, I find that one more branch is left. So I cover a of 0. And then again I go back up and I see that I have completely covered a of 1. But I have another branch of a of 2 left, which is printf 2. So I print 2. Again I go back up and then I have to cover a of 1. So there is a call to a of 0, which leads to nothing. There is a printf and the printf is on 1. So I print 1 and then I go back up and there is an invocation on a of 0, but there's nothing to do with a of 0. So I've completely covered a of 1 and it also means that I've completely covered a of 2. And my final output is 1, 2, 1. My final output is 1, 2, 1. And how many function invocations have I made? If you see, I've made a function invocation to a of 2. That's 1, 2, 3, 4, 5, 6, and 7. That means for a value of n equal to 2, I have made 7 function invocations. So I can say that for n equal to k, I have to make a total of 2 to the power of k plus 1 minus 1 function invocations. So these are, or this is the total number of function invocations that I have to make for a value of n equal to k. So you see here the value of k is 2. The value of n is 2. So you put n equal to 2. So if you put n equal to 2, in this formula, what do you get? You get 2 to the power of 2 plus 1 minus 1. So that is 2 to the power of 3 minus 1. So that is 7. And which is the case here? So we saw 1, 2, 3, 4, 5, 6, 7. So I have to make 7 function invocations, which is indeed summarized by this formula. So I hope this helps. What I'll do is I'll take up more examples in future videos to make this concept clear. Thank you.